Band Theory of Solids by Dr. Shekaram, Professor of Physics and HOD of S&S, Mathrusri Engineering College, Hyderabad. The electron theory of solids aims to explain the structures and properties of solids through their electronic structure. There are three important theories which have been developed to explain the structure of the solids. One is the classical free electron theory. It was developed by the scientists Drude and Lorentz in 1900. According to this theory, the metals containing free electrons obey the laws of classical statistical mechanics. The second one is the quantum free electron theory. To overcome the difficulties which the classical free electron theory could not explain, were explained by this quantum free electron theory, which was developed by the scientist Sommerfeld in the year 1928. According to this theory, the free electrons obey quantum laws. The third important theory is Bloch. This theory was stated in the year 1928. According to this theory, the free electrons move in a periodic field provided by the lattice. This theory is also called band theory of solids. Now let us first discuss the classical free electron theory. In an atom, electrons revolve around the nucleus, and every metallic substance is composed of such like atoms. Actually, the interior of the metal is assumed to be the region containing ions, because due to the metallic character or the tendency of losing electrons, or electropositivity of the atoms is more, the atoms that are present in the interior of the metals readily lose the electrons and become ions. And these valence electrons are left by the atoms, and atoms have become ions. These electrons which are given by the atoms are free to move in the space available between the ions. Here the interaction between the ions and electrons is ignored, and electrons will move in the space available between the ions without any interaction with the ions. They collide with the ions, and whenever they collide with the ions, the direction of the flight is changed. Therefore, the electrons move randomly inside the solid. And these collisions are considered to be the elastic. Therefore, at every collision, there will not be any loss of energy. And electrons are randomly moving in different directions. When the electron motion is there, why there is no conductivity of solid in this case? Because in the absence of the external electric field, the number of electrons that move in one direction will be same as the number of electrons that move in the opposite direction. Therefore, the net current is zero. That is the reason why in the absence of external electric field, the conductors do not exhibit any conductivity. This is explained by the classical free electron theory, and the electrons are considered to be the particles of gas. Therefore, the electrons obey the Maxwell-Boltzmann's classical statistical mechanics. This figure shows how the electrons move randomly. At every collision, the direction of the flight is changed, and electrons are again moving till the next collision takes place. The average distance that is traveled by the electrons between any two collisions is nothing but mean free path. Now, what is the success of classical free electron theory? That we can know from this. It verifies Ohm's law. So, the expression for conductivity is derived, and which has shown that the Ohm's law can be verified using this classical free electron theory. It explains the electrical and thermal conductivities of metals. It derives Weidmann-Franch law, that is the relation between electrical conductivity and thermal conductivity. It explains optical properties of metals. There are failures of this classical free electron theory. The electrical conductivity of semiconductor and insulator cannot be explained by this theory, because some are acting like conductors, some are acting like insulators, some are acting like semiconductors. The reason could not be explained by this free electron theory. The concept of photoelectric effect, Compton effect and blackbody radiation cannot be explained on the basis of this theory because these phenomena are based on quantum theory. The ferromagnetism cannot be explained by this theory. It fails to account the facts such as specific heat, temperature, dependence of conductivity and dependence of electrical conductivity on electron concentration. To overcome all these difficulties, which could not be addressed by the classical free electron theory, and a quantum theory has been developed, and the Kronig-Penny model could explain all the problems which are faced by the earlier theory, that is free electron theory. So this theory successfully explains electrical conductivity and specific heat and thermionic emission and paramagnetism, therefore ferromagnetism also. This theory failed to explain many other physical properties. For example, it fails to explain the difference between conductors, insulators and semiconductors, and positive Hall coefficient metals and lower conductivity of divalent metals than monovalent metals. So all these difficulties could be clarified, all these doubts could be clarified by the quantum theory which was developed by the scientists Kronig and Penny. So according to this, the potential inside the metal, according to classical free electron theory, is considered to be constant. But it is not true. The potential inside the metal is not constant, but it varies. As and when the electron is moving in the space available between the ions, when it is moving or when it is going away from the ion, when it is approaching another ion, there will be variation in the potential of an electron. That variation is periodic. The variation is changing with certain period. So it is assumed that whenever the electron is going away from the ion and in between the two ions, the potential is considered to be maximum, and at the site of the ion, the potential is considered to be the minus infinity. So the potential variation is from minus infinity to 0. That is, at the site of the ion, the potential is considered to be minus infinity, and in between the two ions, in midway between the two ions, the potential is considered to be maximum, which is equal to 0. The potential is taken to be 0. It is according to the equation, we can write down that V is equal to minus 1 by 4 pi epsilon naught Q by X. When X is 0, the potential is becoming minus infinity. When X is infinity, the potential is becoming 0. So as and when the electron is very close to the ion, its potential is becoming minus infinity. As and when the electron is considerably at larger distance from the ion, its potential is becoming 0. That is actually the variation, how the potential varies when the electron is moving in the space available between the ions. But this problem with these two values of potential, minus infinity and 0, could not be solved that easily. To avoid the complexity in the problem, the Kronig-Penny have suggested that, or they have modified this model by assuming that the potential at the site of the ion to be 0 instead of minus infinity, and the potential between the two ions, instead of 0, they have taken it to be the maximum, and it is equated to V0, which is actually the maximum potential of the electron which is moving in the space available between the ions. Therefore, the variation of potential is modified to the series of potential wells as shown in the figure. Series of potential wells. These are all periodic wells. The width of the well is taken to be A, and the gap between any two wells is taken to be B, and height of the potential barrier or height of the potential well is taken to be V0. That is, the maximum potential that an electron can possess is V0, and if it is more than that, that electron can come out of that potential well. And here in this figure we can see there are two regions considered, region 1 and region 2. Region 1 is inside the well, region 2 is outside the well and between the two wells. So here we can see in the figure 0 and A and minus B. A is the width of the well, 0 is the origin on x-axis and B is on the other side, so it is shown as minus B, and we can take it as the width of the well is A and the gap between the two wells is taken to be B. And in earlier we have seen that the Schrodinger's time independent wave equation can be applied to a single potential well, and it is a series of such potential wells. Therefore we can now apply the Schrodinger's time independent equation easily, and we can solve this equation for finding the solution for this problem. So here we can see the Schrodinger's time independent wave equation, d square psi by dx square plus 2m h cross square into E minus V of psi is equal to 0. Here we can see psi is the wave function, m is the mass of an electron, h cross is nothing but h by 2 pi, E is the total energy of an electron, and V is the potential of an electron. That is the Schrodinger's time independent wave equation. Now we can apply this equation to this problem of series of potential wells, and we can now write this Schrodinger's time independent equation for the region 1 and also for the region 2 separately. So let us write down the Schrodinger's time independent equation for the region that lies between 0 and A, that is nothing but the region 1, which is nothing but potential well. Then the equation becomes d square psi by dx square plus 2m by h cross square E psi is equal to 0. Since V naught is equal to 0, the potential of an electron at the site of the ion is considered to be 0. By putting V is equal to 0, we could get this equation, d square psi by dx square plus 2m by h cross square E psi is equal to 0. This is equation number 2. We can also write the Schrodinger's time independent wave equation for the region 2, where the total energy of an electron is taken to be E and potential of electron is taken to be V naught. Since the electron is coming out of the well and it is existing in the region 2, so it is having the potential V naught also. Therefore the equation can be d square psi by dx square plus 2m by h cross square of E minus V naught psi is equal to 0, for minus B is less than x is less than 0. That is, the region lies between minus B and 0. Now this gives the equation 3. Here we can define alpha square is equal to 2m by h cross square E in the equation 2, and beta square is equal to minus 2m by h cross square E minus V naught in the equation 3. The minus sign in this indicates that the V naught is more than the energy, the total energy of the electron. Then only the electron can escape from the well. The minus sign indicates that. By substituting alpha square and beta square, we can write the equations 2 and 3 as d square psi by dx square plus alpha square psi is equal to 0. That is for the region 1, which lies between 0 and A, and d square psi by dx square minus beta square psi is equal to 0. That is for the region 2, which lies between minus B and 0. This gives us equation number 6. Now we can write the solutions for these two equations, and the solution of these two equations can be of the form that is shown here. According to Bloch's theorem, the wave equation can have the solution psi of x is equal to e to the power of ikx u of x. Here u of x is a periodic function which shows the periodicity of the solution. It satisfies u of x plus a is equal to ux. That is, the value of u will be same at x and also at x plus a. That is, its value varies with the periodicity of a. That shows the periodicity of the solution. Using Bloch's theorem, we can solve the previous equations by applying all the boundary conditions, and we will arrive at a particular condition. Until and unless this particular condition is satisfied, the solution for the problem does not exist, because the derivation, complete derivation, can't be shown here, and it is out of scope of the engineering first year students. Therefore, we can directly go to the condition, which we will arrive by solving all the equations by applying boundary conditions. Unless this condition is satisfied, the solution for this problem cannot exist. That is the state where we will reach. That solution is nothing but p sin alpha a by alpha a plus cos alpha a is equal to cos ka. Here alpha is known to you, a is also known to you, and k is nothing but propagation constant, which is 2 pi by lambda. And here p is nothing but scattering power of the potential well, that is given by mv0 ab by h cross square. Once again, in this every letter is clear to you. That is, m is the mass of the electron, v0 is the potential of the well, a is the width of the well, b is the gap between the two wells, h cross is nothing but h by 2 pi. And from this equation, we can see that if you go back to this equation, p sin alpha a by alpha a plus cos alpha a is equal to cos ka. The right hand side of the equation is cos ka, which takes the values minus 1 to plus 1. Therefore, the left hand side of the equation should also take the values between plus 1 and minus 1. So, to find out the value of alpha, that is, why the value of alpha is to be determined? Because alpha contains the energy term E. Therefore, if alpha is determined indirectly, we are determining the energy values of the electron when it is lying in the potential well, or when it is passing in the space available between the ions from one ion to another ion. Therefore, to find out the value of alpha, we have to draw the graph by taking alpha a on x-axis. It is shown as k, but it is alpha a, because we have to take p sin alpha a by alpha a plus cos alpha a on y-axis and alpha a on x-axis. Is it clear? We have to take p sin alpha a by alpha a plus cos alpha a on y-axis, and alpha a is taken on x-axis. And these two horizontal lines, one is drawn at plus 1 on y-axis and the other one is drawn at minus 1 on y-axis. These two horizontal lines lie on either side of the origin of this coordinate system. And when you draw the graph for various values of alpha a, the graph as shown in the figure is obtained. See, there is a part of the graph that lies outside the two horizontal lines, and there is part of the graph that lies within the horizontal lines. All the values that lie within the horizontal lines are allowed for alpha a, and all those values which are lying out of the horizontal lines are not allowed. Therefore, all the values that are allowed, which are lying inside the two horizontal lines, are blocked. they are shown by shaded regions. In the second figure, they are shown by the shaded regions. These are all allowed values of alpha A, and the gap between them are unallowed regions or forbidden regions. So there are allowed regions for energy values and forbidden regions for energy values. So we can draw some conclusions from this graph. The first one is, we can see the shaded regions, the size of the shaded regions is increasing with the increase in the values of alpha A. That is, as the energy of an electron increases, it occupies more and more number of energy levels. More and more number of energy levels. As the width of the bands is increasing, the gap between the bands is decreasing. As the width of the shaded regions is increasing, the gap between them is decreasing. That is, the width of the forbidden regions is decreasing. That is the first point we can know from this graph. The second point is, with the increase of alpha A, the allowed energy states for an electron increases, thereby increasing the bandwidth of the bands. The strength of the potential barrier diminishes. This also leads to increase of the distance between the electrons and the total energy possessed by the individual electron. Then the third point that we can discuss is the value of P, that is the scattering power of the well. We can have two values for P. One is 0, the other one is infinity. When the scattering power of the well is infinity, that is, the electron from the well cannot escape. That is, it is bound to the well. And it can be shown that in this case, this case was already discussed when we have discussed the particle in a box or infinite square well potential. When the particle lies well within the well, the particle possesses discrete energy levels. Its energy varies. Right? There can be the different levels and energy increases with the different levels. Right? It was already derived by the Bohr. When the principal quantum number n is equal to 1, the energy of the electron is different from the energy of the electron when it is in the level for which the principal quantum number is 2. That was shown by Bohr's famous atomic model. And by applying Schrodinger's theory to the particle that is lying inside the box or inside the well, the Schrodinger could also arrive at the same conclusion that the particle possesses discrete energy levels when it is present within the well. So that is the case when P is equal to infinity. When the scattering power of the the scattering power of the well is taken to be 0, then the particle will become free. There is no attraction between the ion and the electron. Therefore, the electron behaves as a free particle, and it can be shown that it possesses kinetic energy which is equal to p square by 2m. It behaves as a free particle. So that is